It's my pleasure to introduce today's seminar speaker. Dr. Ying Sun is professor and head of mechanical and materials engineering at the University of Cincinnati. Her research interests are in heat and mass transfer, multiphase fluids, complex fluids. She, for 3 years, until last year, she was also program director of the thermal transport phenomena cluster at NSF. So in the last, few years, she's had the chance to see some really good ideas and probably some not so good ideas at NSF, and I think she probably can, give us some pointers on what things are shaping up to be in the specific area of multiphase flows. But more generally, I mean, her research, I didn't realize it was, I've only encountered her research in the context of boiling and evaporation and so on, but I didn't realize that she had recently done some really nice work on machine learning and with application, and also some work on applications to manufacturing. I had no idea. So I'm quite looking forward to today's talk, and I hope before I should also mention that she is associate editor of the Journal of Electrochemical yeah. And of course, she's also an ASME fellow, and she's been the recipient of multiple awards, including the NSF career. She's been visiting professor at a few universities, Ecole Polytechnique, Princeton. She's got the AFOSR Summer Faculty Fellowship Awards. I don't want to go into all the the entire list, but she's got a very accomplished resume, and I'm really looking forward to her talk. Please join me in welcoming. Thank you.
Thank you. Thank you so much for the invitation. I actually came here 4 years ago, roughly, when I was a program director, just started. That was my first talk as a program director. So I was very nervous talking about my program, was on thermal. And I do a lot of fluid mechanics study and also some additive manufacturing in the context of trying to understand transport processes. So a couple minutes talk about my department, since my role is a department head for students who are looking for a job. We are recruiting. So we founded more than 200 years ago, 1819, and now over 50,000 students. And we're a co-op program that is very famous for having already run over 100 years. And we have the College of Engineering Applied Science. We have roughly close to 7,000 students and 122 faculty members. And Neil Armstrong was actually one of our faculty in the 70s. And so this is my department. We have 4 different programs that kind of keep me very busy. And we have, of course, the main program is mechanical engineering, has about 900, close to 1,000 students. And then we have mechanical engineering technology program. We have a material science engineering program. That's a pure graduate program. We also have a new industrial system engineering program underneath the mechanical materials engineering, and that is focusing on data science and also kind of modern industrial AI type of application. We have about 1,300 undergraduate students and 300 graduate students. Right now, 47 faculty members, and 37 of them are tenure track. So we're recruiting for both ME faculty and also industrial systems, if you're doing those directions. And we especially interested in mechanics. And we hire a couple robotics people, but that's an area we're trying to build. And and also, of course, energy and sustainability is another area we're interested in hiring. Okay. So coming back to my research, I think some of you guys we met in the society meeting. So our lab is called Complex Fluid and Multiphase Transport. We stand at the interface of thermal fluid sciences we're interested in surface science, we're interested in particles, colloids, and recent years, we're doing a lot of machine learning and AI to how can we advance some basic understandings. So applications range from advanced manufacturing, we use inkjet printing as the additive manufacturing route, and also energy conversion storage, we look at flow batteries and battery modeling, transport processes, also thermal management, especially in the context of water energy nexus. You try to minimize energy consumption when you purify water, and also when you use less water when you generate electricity. Oh, so sorry to mention, and of course, students are the people who make everything happen in the lab, and thus, professors and travel and talk to, talk about research. So I started with modeling, and I'm a modeling person. I was trained as a modeler. So looking at heat and mass transfer multi-phase flow with different physics and some molecular dynamics, looking at phase change, and doing like mesoscale, so-called lattice-Boltzmann simulation, looking at some colloidal particle deposition, and also looking at some multi-physics of electrochemistry, looking at some flow battery. This is an example of overpotential on the surface of carbon fiber, looking at some vanadium flow batteries, and also using molecular dynamics with reactive force field, looking at surface phenomena when you have water wetting a zinc oxide surface, and you have zinc oxide is photoactive, and then you have, with or without UV, you have some reactive happening, and you have some reactive wetting happening. So if you look at the multi-scale modeling with time and space, well, it goes too fast. you have the traditional CFD, and you have this mesoscale lattice-Boltzmann, and you also have the molecular dynamic simulation with some reactive force field that account for bond breaking, bond forming, and in this so-called reactive force field, some kind of quantum mechanics simulation. And we were focusing on using phase field or continuum level combined with molecular dynamics, and doing multi-scale modeling with the help of also accelerated mesoscale modeling to look at how the wetting will happen, how the interface, the moving boundary will material deliver to the contact line. So those are the modeling work we do. In recent years, I think we talk about the total internal reflection microscopy, and more, students get involved in experiment. So our lab become a little bit more experimental, more than 50% now doing experimental work. So this is the example of using optical. So if you have an incident light hit a surface, and if it's above certain angle, be totally reflected, and then generate the evanescence wave in the light stance medium, and that is going to have exponential decay. By looking at the intensity, the grayscale intensity of that light, you actually can probe. So you have a droplet. Oops, too fast. You have droplet heating. It's a drop impact study and very slow down videos. From left to right, only thing different is the viscosity of the droplets. And then only the very left one, you actually have the impact, you have the direct contact. So if the grayscale image go into black, that means direct contact. So you probe this nanometer thin air film in a very accurate region, and then you 3D render. So the bottom is, so the top is the side view image, and then the medium panel is the total internal reflection microscopy. I believe you guys are, doing. I look forward to the heat transfer work. This isn't without heat transfer, just room temperature. And then this is a 3D rendering of this total internal reflection. And then this is like a 800 nanometer. So you can get the height profile of single nanometer resolution. And depends on how fast your your high-speed image, a high-speed camera. So it's microsecond temporal resolution of your 3D gap profile. That is very helpful for a lot of, for example, boiling and nucleation and that type of thing, whether the bubble or droplet actually heats the surface. So we use that to probe a lot of interfacial phenomena. The other thing, we started before pandemic, I had one postdoc doing some machine learning work, and the pandemic kind of kept us stay at home. So we had a lot of students start doing machine learning with colleagues. So we tried a lot of different methods. We tried the unsupervised learning using principal component analysis, which is reduced order modeling. We do the traditional supervised learning using convolutional neural network and also transfer learning. And we also did some semi-supervised learning, and we're interested in how we can get data from different sources and image, temperature, pressure, and to extract information, so-called heterogeneous data fusion. And we also know, I think many of us realize machine learning is a lot of data. I was trying to get community to share data and build a data ecosystem. So everybody's experiment, if you want to share your image, and we build a repository that you can share. So this is an example of looking at boiling heat transfer and the critical heat flux prediction. This is the heat flux versus superheat curve. And then when you have the highest heat flux is critical heat flux. And so what we do is using the images as input of the machine learning. And then we do the reduced order analysis. We try to have the principal components of those images. And then we plot Fourier transform and get the dominating frequency and the amplitude of the image. And then we correlate with the heat flux. So, and then we try to use descriptors and we try to extract information from those reduced order. And then, basically that will give you, for example, bubble, number of bubbles and bubble size and that type of things very correlate to some physical parameters. And so why we do that? First of all, and then you can make decisions by data driven, not by physics based. And because boiling is a very complex phenomena, and then we also that can help reduce. So if you look at the boiling image, it's often like 1,000 to 800 pixels boiling image. If you do the reduced order, it gets to very, very small dimensions. That can help you quickly process data and make online decision-making process using those images. And you can also do so-called future prediction, which is using, I will just talk a little bit in the future. So very soon that you can make some decision making. This is if you have, for example, nuclear power plant, for example, you can make decisions when there's some, boiling crisis happen that will help you with online decision making. This is kind of our trajectory of in the additive manufacturing space. We started, this is when I started my career 2006. And so we're really learning from thermal fluid and nanomaterials and interfaces and trying to make a difference in translational, how we can do better, more sustainable, more additive, more looking at manufacturing. So over the years, we have a lot of fundamental work looking at processes, looking at using exotic nanomaterials and looking at three-dimensional or looking at complex fluids or fluid dynamics and working with industry to enable some solar cell and solid state lighting and some tissue printing, and recently working with NASA, trying to do a little bit, 3D printing of for space flight and heat pipes for the the future Mars mission. So so this is an example of the so we started with trying to understand the evaporation process of inkjet printing of droplets with functional materials, and then you evaporate the solvent, and then you have the carrier liquid evaporate, and then you deposit functional materials. It can be electronics or other materials. So we studied the process of the drying process using in situ characterization of observing from bottom and looking at the velocity field, looking at fluorescent microscopy of the life of a droplet, and doing simultaneous simulation using lattice Boltzmann, and also plasma and laser surface multiplication to help improve the status quo to help better deposition control of those structures. And so this is an example of life and write with everything else the same. We print 20 nanometer particles. And so we look at, this is the interferometry data. And the left has more hydrophilic particles and the right has less hydrophilic particles, but everything else remains the same. What you see is the contact line being different because you have a zigzag, you have a zigzag motion in the less hydrophilic region, example on the right, but you have a continuous contact line movement on the left. This is really because of, if you do the force analysis of particle, you basically need more number of particles if you do the analysis of the surface tension force, the static friction, the electrostatic, the van der Waals forces, and also the drag force due to the evaporatively driven flow. You'll find you need more particles to pin the contact line. And when you have more hydrophilic particles, because the surface tension will pull the particle to the center. So that results in a very different contact line motion and a different structure. So companies they're interested in ring structures, and that really like this type of controlled ring structure deposition. And so this is another example of left or right. The only difference is the shape of particle. So what happened with all spherical particles, then we stretch them to become the same volume, just different aspect ratio. And then you see that you have kind of more uniform deposition in the ellipsoid when you stretch particle, and this ellipsoid versus spherical becomes so-called the coffee ring structure, which is so when you have a coffee drop and on the tissue, you will know of the ring deposition, because evaporative driven flow will move the particle to the contact line edge and form a ring on your tissue, so-called coffee ring effect. And so what we do understand is the spherical particles and the ellipsoidal particle, what are the differences? If you look at the forces on the particle at the drop surface, the ellipsoidal particle, they have more adhesive forces, and also they have the more capillary interactions among the particles. And the capillary interactions help them to stay at the surface of the droplet, and the hydrodynamic forces kind of push the particle to the edge of the droplet. And the competition of those two forces will eventually decide or determine how the particle or how the pattern will form. So we did a lot of those pattern formation type of the work. And so it was two-dimensional, and then we moved to three-dimensional. What happened if you look at the three-dimensional structures? And so if you have a nanoporous structure, or just think about paper as a porous structure. If you print, print some electronics on paper, or so this perovskite solar cells, they also wanted to have this nano confinement of how do you have nanoporous and three-dimensional structure in a very precise fashion. So we study that using combined simulation and experiments. And so interestingly, if you have a third dimension, what happened is you have this interesting competition of particle motion, you have evaporation, of the carrier liquid, you have also the infiltration, because the carrier liquid will actually wet the your power structure, and also you have the spreading effect. And the computation of them, if you do the math, what you have is this is a contact angle versus the residual volume, which is how fast the evaporation will happen versus how fast the liquid is going to infiltrate the substrate that you print on. So you can have a really good kind of phase diagram to predict what the deposition will look like based on the evaporation model, and also the particle motion that is driven by both Brownian and also evaporative driven motion. So and then we started working with our more of a biopolymer collaborators and try to do tissue printing. And so what happened is they want to have print hydrogel basically, but gelatin, and then they can do this type of swelling and non-swelling different structures, and to have folding, and then they will do so-called 4D printing. It's three-dimensional, and then after you print, they will swell, and based on how you design the swelling and non-swelling structures, they can fold in different shapes, and depends on to mimic different part of the tissue. So what we did is helping them to understand how do we do like biopolymer printing, and with different swelling ratio to control the deposition process, and how that structure will affect the final folded structures that cell niches. So if you look at what they're printing, right? So from a complex fluid perspective, and we have water, and then we have glycerol, so it's bisolvent, and we have the gelatin, which is fish skin, and then dissolved, and then we make them more hydrophilic. We make the COH group, carboxylene group, and then we have some surfactant. So it's a very complex process. And when I look at what is the physics involved in this process, I think you guys are a graduate student, you probably know what is a Marangoni flow, right? So that's a surface tension gradient driven flow. And if you look at what happened in this droplet, and when you try to print biopolymer, which is gelatin, and then your water will evaporate, your glycerol is not going to evaporate, so you have a glycerol rich region close to the contact line, and then in the contact line will be pinned and not moving, and your biopolymer will accumulate more on which is the dots here, more close to the contact line, and then they will kind of gel, and then you have also the surfactant is all redistributed. You will have more surfactant in close to the contact line, and then you create the surface tension gradient along the drop surface, and you have the surfactant Marangoni, you have the polymer concentration being different, causing another surface tension gradient. And so it's a very interesting, complex problem that we try to understand. And you do see that with or without the surfactant, you have very different deposition structures. The top one is the one without surfactant, and the bottom one is with surfactant. This is better. So, and then you can see a dome shape versus a volcano shape structures, and you wonder why. And so we look at left and right, one is without surfactant, one is with surfactant. We try to do control experiment, always do the experiment, but just changing one parameter at one time. And then you do the so-called interferometry, basically looking at the
the surface of the drop and look at the height profile through the fringes, and then you get the height profile with time. And when you have more liquid and then eventually evaporate, and what you see is you see the evaporation happen, and then you have very different you have a so kind of inflection point and becomes a very different shape when you put surfactant there. So usually this is interesting because counterintuitive in the sense surfactant is usually helping you to create this Marangoni convection that suppress the so-called coffee rain effects. But this one doesn't seem to help me. So we don't know why, but why is different from the traditional coffee rain. So we try to understand what's going on. And so what happened is when you have a colloidal drop, sessile drop evaporation, you have a larger evaporative flux at the contact region. And then it will cause the evaporative driven overflow. And then you have more water evaporated, you have a like a lower surface tension and also a more solute rich region in this contact line region. You're causing a Marangoni flow from contact line to the center of the drop. However, due to the very large polymer content, you have a gelation in this contact line region and causing the local gel very close to the contact line. And then your strong Marangoni will just circulate around, recirculate, and causing a stagnation point in this kind of closer to the contact line and causing a zone that is eventually, when the water evaporate and also current liquid evaporate, you'll form a volcano-shaped deposition. So this, we did some PIV study. We realized looking at different planes and of the drop and your different slices in the Z direction, and then you do see that there's a stagnation line. You have a gelled region near the contact line that there's no velocity, but the particle is moving, and then depends on where you are in the space, and then you can move. There's some evidence of this recirculation happen inside. There's a circulation flow as illustrated here inside the droplet. This is very interesting and kind of counterintuitive, and is a result of biopolymers. They actually gel at the close to the contact line region and causing the deposition being different from a regular suspension that we experience. And based on that, you can look at the competition between Marangoni force and also the viscosity that is basically the evaporatively driven flow. And then you can have different kind of phase diagram looking at different shapes and compare with other people's experimental study, and we get pretty good interesting results. And recently we're doing this is I think the NASA ESF project, early stage innovation project, is to print 3D printing of titanium and to this heat pipe, a loop heat pipe, which is basically you can drive more liquid and less longer loop and less contact. So you need a lot of time heat loss in the contact regions. A lot of the surface contact, you minimize the contact, and then you try to have an all-in-one titanium panel that with the radiator and also the heat pipes. So this is through a 3D printing process. So this is the cross section of the very porous heat pipe that we print. Is you try to control as small of the wick as possible, like 5 micron pores, and to make. So this is the project that we are trying to do to have a very high conductivity and also have a very small contact resistance due to printing this structure of titanium. Lightweight, high temperature loop heat pipe that in one build. So Here I show some experimental work in the context of, I believe, I think with some of you, I think we talk about the liquid infused surface. Yeah. So this is also the liquid infused surface that we are interested. And so what happened is if you have some lubricate infused surface, so you have some micro and nano structures, and then you put kind of a lubricant in there, and it's a wet surface. And originally, and this is a nature like a pitcher plant. And when you're wet, you have the surface becomes super slippery. And you can use that for different applications. I think even anti-icing, or you can use for self-cleaning surfaces, right? So our interest is more from a fundamental fluid dynamics perspective. If you put droplet, if you spray droplets on those type of super slippery surface, what is the impact? Like, what do you study? Do you have direct contact, or you don't have direct contact? What happens if the film will fail, right? So what we use is using this total reflection microscopy that I kind of introduced at the beginning, is that we try to study the failure modes of the droplet interact with the surface. So the left are the possible the failure modes, the contact modes for dry surface. So you either bounce if the drop is, velocity is small, the Weber number is basically so small, which means your impact velocity is small, and then you bounce. If you get, increase your velocity, and then you started to having failure, you started to, the droplet will hit the surface and make direct contact. And when you have a lubricated surface, which is, you can think about is an atomically smooth surface. So we make the lubricant very, very, very viscous. So basically it becomes a super smooth surface. And then we really use that to study what happened with the different contact modes. And so we use this total internal reflection microscopy and probe the air layer between the droplet and the surface. All right. So this is an example of drop. So the drop is about 1 millimeter in the radius, and then we put it, and this is the total internal reflection microscopy, and then you can see the air film as a function of time. This is the profile, and then we study the history of the contact, and you have a basically when you have enough disturbance, you create this kind of pyramid shape, which is capillary wave, and the capillary wave will make it invert to a a cavity, and the drop in the middle, you would form a cavity or air bubble in the middle of the drop. And then you will have some, well, this is a very, very thin, 100 nanometer or smaller than that. And then you have some disturbance and make it so-called the thin film instability. And that will causing the air film to fail. And then you can see the direct contact between the droplet and the surface. And then you will see the purely dark, which is what happened. This is zero thickness. Yeah, it's a very slowed down video that you can see what's really going on of the schematic we draw here. Yeah, so this is pure dark, meaning you have a direct contact, and then you have some track bubbles. We're going to talk about that in the future as well. So we study a different Weber number of the water droplets, and we study the unstable and stable film, whether we have a bounce, bounce back, or we actually this is bouncing regime, and this is actually a contact mode. This really depends on the thin film instability theory that is related to Hamaker constant and also the surface tension. And so what we see is you'll have stable film when your experimental, your wavelength is smaller than the critical wavelength. and you will have unstable when the wavelength is greater than the critical wavelengths. And so what you see here, I think I showed the video at the beginning, is from left to right. The only thing change is the droplet viscosity. You have water and on the left, and then you increase the viscosity with everything else the same. And then you see what happened is the capillary wave will be dumped when you have a higher viscosity, higher viscosity drop. So you have the attenuation coefficient, which is different, and it's a function of viscosity of the liquid. And you'll have either your capillary wave will be dumped that result in no failure, and or you don't have any damping effect in the capillary wave that causing the failure modes. And this is kind of the failure modes that we see. So I think if you can, we really look forward to the boiling study.
No pressure.
Well, I feel like you give me a lot of pressure when you introduce me. Now it's a pressure back to encourage you to do the heating work. So this is, again, we did not have the heat transfer. This is a purely fluid dynamics. Because heat transfer is more complex to control everything. The temperature, you have everything uniform and as a heat flux that you want. Okay, so this is again the same thing, but we just look at the history of basically the color shows the high profile, and this axis is the time. So basically the size of showing you how the air film, profile look like as a function of time and how it moves. So it's very powerful. You just have to set up very clean, Yeah. So, and then, we study different contact modes. So we study contact modes, and then we study how after the contact, what are the kind of the post contact. And then you sometimes trap all the bubbles, and we wonder why. I think we talk about the ice in here summer, you don't have any bubbles in the middle, and then that made me think a little bit about the trapping of the bubbles when we had dinner talking about this stuff yesterday. So what happened is so you can see some bubble entrapment, and we find this is related to the contact length velocity and how, basically give you the capillary number of the contact length velocity, and then how that when you above certain threshold, it will trap bubbles, and below which bubbles will actually not, you will no longer have those trapped bubbles. And so then what we change is the decreasing the surface tension of the liquid. And what you see is, and then by decreasing the surface tension of liquid, your threshold, will change, that causing the, when you decrease the surface tension, and you actually, the threshold will increase. So that causing, basically, you will not have any trapped bubbles by just changing the surface tension of the fluids that you're wetting. So just to summarize this part, we're very interested in fluids. I really want to share a lot of the fluid work that we do. Is we study using the total internal reflection microscopy, and we study the pre-contact air film stability and the contact modes. We also try to understand the post-contact, the wetting phenomena, and also the bubble entrapment, and how that will be related to the viscosity of the liquid and the impact velocity that change the wetting phenomena. And this is, this is a very interesting work that we have done. I hope this can be extended to more in the heat transfer community very soon. So recently, another interesting thing we just started doing, last month, we got a new project looking at using acoustic sensing to study flow boiling and condensation. This is under microgravity in the International Space Station. We believe that, you know, at acoustic sensing, basically you listen, you have a higher, you can probe using higher frequency, using either acoustic emission or microphone or hydrophone in the liquid, and to study, so because you can actually probe compared to optical imaging, a bigger range of frequency. We hypothesize that a lot of instability, including that triggers the critical heat flux in the boiling, is related to some high frequency instabilities. That we hope to use acoustic sensing to detect some interesting interfacial instabilities, and also in microgravity, a lot of these instabilities are separated in nature, so are decoupled inherently. So that's something we look forward to using the NASA setup, and then we put basically the acoustic sensor. So those are the NASA existing facility at the International Space Station. So one is a flow boiling module, one is a flow condensation module. Those are built, and you know, tens of millions of dollars to build this type of setup. And what happened is we put in, this is the setup, we put some acoustic sensor, microphone, and acoustic emissions, basically looking at the stress wave, but outside the chamber. And using that to study, we can put multiple optical sensors, the acoustic sensors, to give us a little bit background, a little bit understanding of what's going on, and helping us to look at the different, to decouple some of the physics. Some preliminary results of flow boiling, now we see that it is you have, this is boiling, nucleate boiling versus transition boiling and nucleate boiling again, when you have heat on and heat off. And you will see some sound signals being different, and you can see the acoustic basically emissions, which is a stress wave, will give you different signals when you have different regimes. So, and then we have an expert from acoustic aspect, and then helping us with signal processing to decouple some effects. So a lot of things going on, and a lot of unknowns. And so we have some preliminary data for boiling, and nobody, if I understand, so far I haven't seen anybody did any acoustic sensing for flow condensation. So we're trying to explore that space, whether we can detect anything interesting. I'll be happy to report it hopefully soon. So I don't know how much time I have. How much time I have? Or it's over? It's over. Okay. Okay, 5 minutes. That's great. So now we talk a little bit about this machine learning. So we use, well, boiling is a very good example of what we thought would be good to use machine learning, because the physics is so complex, right? So I mean, the pure physics-driven work will be difficult to really understand how, you know, different instabilities, and everybody seem to be not agree with some of the mechanism. I think, you know, so we thought, okay, let's give a chance to really, you know, see what machine learning can do for us. So one thing we were doing is so-called, you know, we try to do so principal component analysis, which is unsupervised learning. So we did not train the data. I mean, we did not train the model. So what we did was looking at, for example, image, and then we know the dimensional image, and then we try to correlate data and find the most dominating principal coordinates, and then we look at the components, and we see how, you know, whether we can cluster data using different classes. And that will help us. So this is traditional supervised learning. If you can think about a cat and dog type of, basically, how do you, you know, from the bubble image data set to bubble statistic in terms of bubble size and count. So we don't do any of those tagging. So what we did was just, having input are the images, and then we do the principal component analysis, try to find the dominating parameters, and then we try to interpret those dominating frequency and dominating amplitude and correlate with the bubble size and count or other parameters. And that really help us to kind of separate the significant and insignificant features and extract some very important signatures and becomes computationally less expensive. So this is, for example, nuclear boiling and critical heat flux. And then we look at the dominating frequency of these images. We did not train, we just, feed the model. And then we see when you have critical heat flux, you have a big jump. This is with heat flux and big jump in this dominating frequency. And then we try using different surfaces. We have some different data sets from us in-house, from other universities, collaborators with copper, plane surface versus microporous surface with different foam structures. And when we find is a lot of interesting thing, you do detect this regime change of the signatures directly from images without any physics involved. So this is the example of what we do with supervised versus unsupervised learning. And supervised learning, you basically have to tag and train the models, and then becomes really tricky. Your error becomes really, really large uncertainty because you manually, for example, the size of the bubble, you cannot really, tagging very, very accurately. So you have this big error bar. But in this, without any training and using this reduced order analysis, you get a much better clean data, clean clarification. So, and then it's interesting, not only for the water, we also extended to low surface tension fluid and coolant, for example, HFE. This is a 3M refrigerant, and you can see the capillary numbers and things, capillary lengths all changed, but you have a lot of interesting different phenomena. But when you do the machine learning work, you get signature, very clear signature when you have a regime change from the just purely image processing, or image processing, the principal component analysis study. So I think if you haven't tried, it'll be worth trying. So we're very excited about these results. I do realize that the future, of course, is to have more physics-informed, physics-integrated machine learning. But this is a pure data-driven. It gives you some very interesting insight. So I know my time is out. I should stop. And with that, I really appreciate it. Thank you.
Thank you. Yeah, we have time for some questions, but I'll let you moderate.
Oh, sure. Any questions? Yeah.
Thanks, Ying. That was a really, really interesting talk. On the droplet impingement, the dynamics of the droplet as well as internal bubble formation were really complex, but it looked symmetric. I was wondering if you have a glancing angle of impingement.
Yes.
How much did the dynamics change?
Yeah, I think we studied that. Well, okay. So so interesting. So what happened is you have to set up, if you have an angle, you have to set up your everything a little bit angle as well, I believe. Yeah. So Yeah, so basically your left and right still symmetric, your up and down will be different, right?
Mhm.
Yeah, so things, I think we did some study, maybe I can share offline with you. Because of, we never published, but we have some results. And, so I think at the time there were other people interested in this. I mean, how, yeah, so that was driven by self-cleaning surfaces. I think if it's John Bush at MIT or he did some work, I mean, in the fluid meeting, I don't know you guys remember. So I don't remember on top of my head what are the, but that actually kind of, we did not started with the total internal reflection. We were just doing the inclined surface and some kind of liquid infused or lubricant infused surface. And somehow, one student and started doing, and then the direction changed. It is like always going somewhere. So to answer your question, I don't right now on top of my head remember exactly what are the differences. Yeah.
Okay.
Yeah, you do have gravity, right? So you do have, yeah. But I remember that was an APS fluids meeting. I think was some group talking about, and we started doing at a different context, and then one thing lead to another, and we totally changed our our direction of study. Yes. Yeah. Yes.
Professor, for clear and better, you are measuring the thickness of air film? Or
Yes.
just
Yes.
air film?
Yes. Air film.
And what's the time scale under which you are observing?
Yes, so I think I have timing of the video, right? So the time scale, and you can see those are really, for example, I can show, this is the example, and oops. So the video is, this is millisecond, I don't know if you can see. So I think we're using high-speed camera, and we take, this is a much slowed down video, of course. So yeah, it's very short. I think it's several milliseconds. And you wait. Yeah. Yeah, so that is of course, so we dimensionalize it, you pick the capillary time scale. And in the publication, but this video is not the non-dimensionalized time. It's real time, but it's slow down video. Yeah, so you can see the about 5 milliseconds that contact happened on the left. Yeah, which is a water droplet. And then you increase the viscosity, and this capillary wave will be down. Will not trigger the cavitation, and will not trigger the thin film instability, thin air film instability at the bottom. So if that explains. So go ahead.
So the principal component analysis, it's a matrix. You are taking an eigenvector essentially,
Yes,
and that's going to give you some vector, some shape.
yes.
Does that shape match, the contact line of bubbles
Right.
where the heat transfer is maximum, or is it more random than that?
Yeah.
Which is what I would,
Yeah, it's very, so good question. So if you look at, this is what you see from, okay. So, this is reduced order image, but you actually get more, but you don't exactly, so this is, so what we have, reduced order image is the same as, so it's not exactly the bubble. It's kind of resembles some of the, but it's more of the boundary of the bubble, and also the size of the bubbles. But you don't have, so the bubbles are not moved. If the bubbles are not moving, you don't get it. So it's interesting. Let me show you what happened is, so
and then you reduce the dimension, and then you can do so-called, so this is the trick that we did. It is a so-called long short story memory, which is how when you do like Google search, whatever, now you always have those, so language processing. So this is to predict future. You can, based on the previous time step, and then you can see what the boiling would look like, or this is reduced order, and then we can use that to get back to the kind of the real dimension. So, but you can only do very short time.
Yeah.
Otherwise, the arrow will go quickly bad.
Right.
Yeah, so that model has to be improved.
I think the reason I asked was because there are, if you go back to 1990 something, Kenning, with liquid crystals, he actually used non-orthogonal functions.
Yes,
Which are actually like circular,
okay,
and those seem to do a very good job of, with this limited data set,
yeah,
of getting the fields right for, as opposed to PCA, which is more like a Fourier analog,
yes,
no directionality, but no
Yes.
structure.
yes.
Whereas, the bubble, the field has structure.
Yes, so I have to be honest that our data science people don't feel the PCA, they think the PCA is only give you a leading order and not good enough.
Okay.
So like you mentioned, you have a lot of, from a data science perspective, like GAN, which is, so a lot of other methods are much better than PCA. So, because we only use the first two, and then
Modes.
you can use like 10 modes and more modes, you'll get more accurate, but then become more expensive. Yeah, but I feel for our interest, it's good enough, happen to be. So, yeah, I think it's not cutting edge it's an existing method, be there for a long time. But it happened to be effective in our context. So, yeah, so it is good because it's very, they reduce your data set and very significantly. Yeah. But you're right, we haven't tried non-orthogonal, solver. And the other, I think we did other generative adversarial network and other kind of work. And nowadays, computer scientists are saying, we don't use GAN or other method, we use all this, the ChatGPT stuff, like the language models.
Right.
Yeah, so again, these things change so quickly, we
are behind.
we're behind. So we're using the established algorithm in our context. Yeah, go ahead.
So what's the time scale that this prediction works?
Yeah, yeah, good question. So again, this is based on that particular model. It's called a bidirection long short time memory. And I have to say, at that time was like you can only do like whatever 200 frames after your your previous 200 time steps in the future. But again, I realize, as I mentioned, this new machine learning model change all the time. If you ask me, maybe this we did a year and a half or a year ago, if you today's model maybe is very, very different. And if you do that, if you go to like GitHub and then download the best, and right now today's, because those things change like every day. So I don't know what it can do now, right? So those machine learning algorithm used in different applications and depends on the model update, and you have a big community. If you go to GitHub, for example, and you change something, you publish yours, it's open source, right? So I don't know what it will be today, right? So it's constantly changing. That is why I think students, I'm not suggesting, but it it is something, an open-end question you can always try. So I guess we have to move on somehow, but I have to say, it was very very new for the natural language processing, large short memory, long short memory, time memory is part of the natural language processing, and then that's related to when you do the search of language. That's how you can predict for future. That's how you search and suggest something, right? But then you also have different ways to do that now. So I don't know what is the most powerful, what you can do now. It is a moving target. Yes.
Last question.
Okay,
Yeah.
yeah, Professor Sun, fascinating talk. I have a question about the experimental conditions. Can you give some comment on
This
like
is
the control experimental conditions
Oh, yeah,
in your machine learning? You're talking about collecting like data from several groups,
Oh,
build a data bank, but I don't know machine learning too well, but I feel like if for example, the surface roughness is not controlled the same between different groups, so their
Right.
data inherently will be different. For example, the
Right.
bubble generation rate. So in your
Yeah.
machine learning models, will you put all the data together regardless of the experimental conditions, or you give some categorization to the
Yeah, so,
experiment?
we think, the model should be universal, right? Should not be dependent on the structure, even to be independent of the working fluids, and should definitely be independent on the surface textures. So, I mean, you try to, detect some, more of a general, trend. Yeah, but again, I feel in the future, it's still a combination of data and physics based. It can detect some regime change, but it probably will not give you a very quantitative heat flux versus image. You cannot see the boiling image and tell me what's a heat flux without doing any thermal measurement. I don't feel we can be that accurate. We try to correlate the image with the heat flux, but it's not going to be that accurate now, I don't believe. So basically, if you get some image, you would try to predict what is the instantaneous heat flux from this image, from looking at the boiling image. But I don't think we're there yet. It is an effort to try to get some, or, okay, so the reason we started doing acoustic wasn't because of this microgravity, it was because I think an IIT, a professor published a work using acoustic hydrophone and to study purely from the hydrophone signal to study the boiling correlation with heat flux. So, and then we feel like, oh, this is interesting. So because the cameras are expensive, but putting a hydrophone in the water and detect the boiling is very easy to do. And they get really good correlation between the hydrophone signal with the heat flux, instantaneous heat flux. So a lot of possibilities you can do. I think I guess I did not answer exactly your question, but I was just fascinated by all kinds of. So we saw that, and then we implement in a different context, and then we use that to study the instability of interfaces. Yeah, so I kind of move around a little bit. I like to kind of thinking about the problem in a different context.
Time's up.
Yeah.
I'd like to thank Dr. Sun for an excellent talk and very stimulating. Thank you. If anyone has more questions,